Welcome to the first lecture of the course Multi-View Geometry for Computer Vision Applications. The team of the course is, the lecturers are Ronen, Yoni, and me, Meirav Galun, and the TAs are Hodaya and Amnon. I really appreciate if you'll turn on your cameras. It will be nice to see you all. Good morning. The outline of the lecture today will start with some general course information. Then we'll have some introduction to computer vision, very short one. And then motivation to the main goal of the course. We'll cover some topics, including camera modeling, camera motion, camera calibration, and projective geometry. We have in this semester 14 lectures, started at 9:15. Please be sharp at time. During the semester, we'll have between 5 to 6 mandatory assignments, which will be 40% from the final grade. And then we'll have some final project, practical project, in-depth learning, and related to the material of the course. There is a new model of Weizmann. We are going to use it. All communication will be through this model. It seems convenient. I hope so. During the lecture, we'll present some exercises which are optional but are quite helpful to follow. So we suggest to try to solve them. In general, you can get some suggestion and get some advice in group in order to solve the assignments, but each assignment should be individual. You should submit it individually. We really expect that you will be present in 80% of the classes, and please turn on your cameras. It's nice to see you and to understand who is speaking to you. So you will, through the Weizmann model, you will get all lecture presentation, and then we'll also cover some scientific paper in the course, mainly in deep learning, and you have the access to them. Essentially, we mainly follow the material of the computer vision course by Carl Olson from Lund University. And we asked him for permission. It's fine with him, and we really appreciate his permission. In addition, we use the Bible of multiple view geometry by Hartley and Zisserman. It is available online, and you can use it if you want. So let's dive to the first slide of the course.
Question, Meirav?
Yeah.
Is the material changed from last year course?
Yes.
Okay.
Not very much. Did you take the last year's course?
No, I just asked people how was it, and they recommended. So.
Yeah, I mean, mostly it's a classical 3D reconstruction formulations and. But we added some deep learning stuff, recent work on that.
Cool, thanks.
Yeah. Okay. I mean that if somebody took it for credit last year, he cannot took it for credit this year. That's maybe. But if you didn't take it for credit, you can take it for credit, of course.
Can we use the video? Recorded videos on a
yes, sure. You will get the recorded videos, sure. Yeah.
But from last year, are they still relevant?
You can use if you want. I don't care if you
say that it would capture. So last year we had, I think, 11 or 12 classes, right? I don't remember exactly. And there will be some changes, but most of the material is the same. So you can use it, but there will be some additions here.
Thanks.
And I think another question, will this course be in MATLAB or Python? Because I think last year it was in MATLAB, right?
The course will be in MATLAB this year. Yeah, again,
Thanks.
MATLAB.
No, but we will have the project might be in Python.
Yeah, the project, yeah.
And we might have another small assignment before the project in Python. So the original exercises are in MATLAB, which we borrowed from
Damage.
Yeah, so
In any case, I would suggest to attend the lectures, the Zoom lectures, and to listen to the lecture we are going to cover. Sorry? We're going to cover this semester, and enjoy the lectures. Any material will be delivered for you, so everything will be okay to follow. So what is computer vision? Actually, there are two related fields. One is computer graphics and one is computer vision. In computer graphics, generally you have a model and you generate images from the 3D model. In computer vision, you try to solve the inverse problem. You have images, 2D images, and you would like to generate the 3D model from the images. This is the main difference. The main goal of our course is multi-view reconstruction or structure for motion. You have many images of a static scene, like what you see here on the left. This is 4 images out of sequence of many more images. The images are captured in different times and viewpoints, and the goal is to solve the structure for motion problem. This means that given the images, you aim to recover the 3D structure and the camera poses, like what you see on the right. Okay. So let's look from very high level at the pipeline of the multi-view reconstruction. Sorry, no, before this, just to before you're going to see the pipeline of the structure for motion, let's try to understand why structure for motion is challenging and what are the useful application of structure for motion. So recall that the input to the problem is only 2D images, which are perspective projection of the 3D scene. Then we have to take these 2D images and we have to move back from the 2D world to the 3D world. This is without any prior knowledge on the 3D scene and without any knowledge on the location of the camera. This problem is relatively challenging. Relevant applications are navigation, autonomous driving. Also in medical imaging, you can use 2D to 3D for surgery guiding, augmented reality, photo organization, etc., etc. There are many applications. So now let's dive from high level to the multi-view reconstruction pipeline. So in general, you have many images. Here you see only 2. And the first task is point detection and matching between the images. So you first detect interest point or key points in all images, such corner, edges, etc., etc. And then you try to match between the images according to this matched point. Finally, when you have the matched point, you are able to compute the 3D position of this matched point and also the position orientation of the cameras. Essentially, the last part of the pipeline, the 4th part, is the main part of our course. We are not going to deal with the point matching and the detection of key points, etc., etc. So I would like that you'll see the movie given by Carl Olson for the pipeline of structure for motion. I think it's very nice to look at it without sound. First part, you take many images of some static scene, like what you see here. Then you identify the key points from the images, like edges and corners. And then you try to make correspondences between the images for these key points that you searched before, like you see here. Then you are able to compute the camera position and the 3D structure. Here you see triangulation between a matched point. We'll cover everything which is related to this. Finally, you can see the 3D structure and the location of the cameras. And as you see, the structure is sparse because it's related to the matched point, and the matched point do not cover the entire images. So you can then make another pass and get dense reconstruction like here. Somebody with the... Okay. Can you please mute yourself? So the main part of the course is covering...
Can I ask something about what you just showed?
Yes, sure.
The final result here is a model or images that projected for something. I don't know, like the video at the end.
I cannot hear you well. I cannot hear you well.
Oh, the video at the end.
Yeah.
Yeah, the video at the end.
Yeah.
Is images projected for a model. Like my question is, how do you represent the model? How
the model? The model is represented. The model is represented by 3D position of points, like you saw before. This is the way to present the model.
The sparse reconstruction is a set of 3D points. The final reconstruction is a mesh, usually.
That's what you asked?
Okay, thanks.
Okay, no problem. Okay. We mainly speak about the sparse reconstruction, and also then we'll speak about some dense reconstruction, but the first part of the course is mainly the 3D sparse reconstruction. So the main part of the course is the recovery of the 3D position of the match point and the position and orientation of the cameras. We'll have some theory and classical tools, and also some modern deep learning techniques. As a teaser, what you see here is some result obtained by a research that was done very recently in our group using deep approach. On the left, you see example of the images that we input to the approach, to the algorithm. And on the right, you see the 3D reconstruction, 3D sparse reconstruction of the church. And the red pyramids stand for the location or orientation of the cameras. Okay. Now we move on to speak about the model of the camera. I guess that part of you, or many of you, took the computer vision course last semester, so maybe for part of you it will be boring, but in order that everybody will be on the same page, I'm recovering it again. So the very simple model for the camera is the pinhole camera model. So camera actually maps between the 3D world to 2D images, like you see here. The pinhole camera model is very useful. In general, you have a box and you have a hole in the box, and the light from the object is projected to the back wall of the box, like you see here. Mathematically, what does it mean? I'll try to illustrate the mathematical model of the pinhole camera. So in general, you have a camera coordinate system denoted here by EX prime, EY prime, EZ prime. The origin of the camera center is, the camera center is located in the origin. This is the pinhole. The image plane is located at Z equal to 1. And the line between the camera center perpendicular to the image plane is called the principal axis. Then you'll have the point where the principal axis cuts or intersect the image plane is called the principal point, and the plane at Z equal to 0 is called the principal plane. It's equal 0, which means it's parallel to Z equal 1 and contain the camera center. It's called the principal plane. Now, regarding the projection. So let's say that we have a scene point in the world. We denote it by X with 3 coordinates. We call the ray between the camera center and the point, we call it the viewing ray. And the projection of X on the image plane, we denote it by small x. Actually, this is the intersection between the viewing ray and the image plane. Okay, any question? Okay. Now, let's try to model mathematically the projection of X on the image plane. So we can parameterize the viewing ray by C plus S, which is scalar, time X minus C. Since C is exactly 0, we get here S times X. Now the viewing ray intersects the image plane exactly here. So Sx3 prime at the third coordinate of Xx should be equal to 1, and therefore S is equal to 1 over X3 prime. Okay? Therefore, the projection of X onto the image plane is exactly X1 prime divided by X3 prime, X2 prime divided by X3 prime, which is located on the plane Z equal to 1. I think that in the computer vision course, you make this derivation using Dimion Meshulashim, similarity between triangles. This is you'll get the same result. And also another issue is that if the image plane is located as Z equal to F, then S would be F divided by X3 prime, and then you get the point which is here. Okay, everything will be multiplied by F, like you see here. Okay, I guess it's clear because maybe we are familiar with it even before the course. Okay. Sorry, just a minute. Okay, this is a naive exercise that you can try to do it later on to compute the image of the cube. Let's move on. Okay, so in general, we have a static scene, but as you understand, the images are captured from different views, and we have to take some reference coordinate system in order to refer to some global coordinate system, which means that in order to characterize each camera, this is one camera and this is the world, we need to characterize the camera with respect to some global coordinate system. So from now on, all camera movements and the scene points will be related to this global coordinate system, okay, which is denoted by EX, EY, EZ, okay? So, okay, a camera can undergo rotation and translation, which means that each point in the local coordinate system denoted by x1 prime, x2 prime, and x3 prime can be calculated given some point in the world by rotation followed by translation. Okay, rotation of the point followed by translation. The rotation matrix is an orthogonal matrix such that the determinant of the rotation matrix is 1, and the translation vector is a vector in R3. Okay, now using a homogeneous coordinate like what you see here, we can take R and T and block it in a matrix. We call R and T the camera matrix. This block is called the camera matrix, and uses this representation, which is called homogeneous coordinate representation of the 3D point. We can write it. We can write the formula of moving from the global coordinate system to the local coordinate system with the prime. We can write it like this: RT times the homogeneous coordinate. Also, what you see here, just a minute, is that from the one hand, you get the local coordinate values of the point in the world, in the local coordinate system, in the left system. But on the other hand, you essentially, if you take out x3 prime, you get the projection of the point onto the image plane. So this result have two, I would say, faces, like I should say in Hebrew. You essentially you get the local coordinate system and also the values in the local coordinate system, and also the projection of the point on the image plane. Moreover, I guess that you remember that the rows of the rotation matrix R encodes the x prime axis, y prime axis, and z prime axis of the local coordinate systems as expressed in the global coordinate system. Is this clear? My last, everybody is familiar with it? That if you have rotation matrix, essentially the axis of the local coordinate system, the rows of the rotation matrix actually determines the axis of this system in terms of the global coordinate system. Everybody familiar with it? Is it clear?
I don't understand it.
You don't understand it?
No.
Okay. You see that actually, what is the operation here? Operation here, it's take R and multiply by a vector. What does it mean? It means that you take every row in R and you multiply it by the vector, and you get new values, okay, of the local coordinate systems, okay?
Okay.
Okay. In order to do that, you have to express somehow what are the rows of the rotation matrix. Essentially, the rows of the rotation matrix are the coordinate of the local coordinate system, okay, as expressed in the global coordinate system. Otherwise, this dot product or inner product between the rows of R and the vector in the global coordinate system would not let you have the values, the new values on the local coordinate system.
Okay.
Okay?
Which is the local?
The left is the local. The right is the global. And in the camera motion, you would like to take each point in the world, you note it here by a dot, and to express it, to move from x1, x2, x3 to x1 prime, x2 prime, and x3 prime, which is the representation of the point of the 3D point in this local coordinate system.
And why the leftmost representation is useful?
Why what?
The one with the X, the leftmost representation here is useful.
Because you would like to understand what is your how you project your 3D point to some local coordinate system, to some camera. You have many cameras, okay? And each camera is given in its local coordinate system. You have to move between some global reference to the local reference and back. Otherwise, you won't able to get something which is consistent and coherent to understand what is happening.
Right, but here in the leftmost representation, you take the x3 prime out.
Ah, right. I'm taking.
So why is that?
Just okay. I just told it. I told the following thing. In order to get the representation of a point in a 3D world, I make the following step. I take the camera matrix RT and multiply it by the representation of the point in the 3D world and get a new representation in the local coordinate system. This is the red one. This is clear?
Yeah.
Okay. Now I say this has another explanation, another interpretation, I would say. If I'll take out x3 prime, I'll get, and I'll look at this vector, the vector in the parentheses,
Right.
I'll get exactly the projection of the 3D point onto the image plane. Okay?
Thanks. Yeah.
Okay.
It's on the ray, right? It scales by x3 prime.
Right. That's what we saw before. Yeah. Okay. So I'm recap. If we have local coordinate system and global coordinate system, we know how to move between each to the other. Okay. Just to say that R and T are called the extrinsic parameters of the camera. This is in opposed to inner parameters that we'll see later on in the lecture. The matrix RT is 3×4 and is called the camera matrix. And now I have a question. What is the camera center in world coordinates? Can we solve it? Anybody has an idea how to calculate the camera center in world coordinates?
T?
Okay, let's hear.
T?
Sorry?
The vector T?
Not exactly, but related. Let's see.
Minus the vector T rotated?
Exactly. So let's see why. You say it. Okay, so if x prime equal to rx plus t, it's equivalent to x equal to r transpose x prime minus r transpose t. Why? Because I'm multiplying this equation by I transpose, and since R is orthogonal matrix, I get this one, this relation. Now the camera center in local coordinate system means that x prime is going to be 0. Therefore, this is cancelled out, and I'm left with this one. The center of the camera in the world coordinate is exactly like minus R transpose times T. Okay? And what you see immediately that actually C1 transpose is in the null space of the camera matrix. It means that if I'll take the camera matrix RT and I'll multiply it by C1, I'll get exactly 0. You can see it immediately, okay? Now, I would like to introduce another version of camera matrix. So far, we discussed the following operation. We take X, rotate, and add translation. It's written in block formulation. It's written like this. And we just saw that the center of the camera in world coordinates is exactly, just in the previous slide, is minus R transpose T. Now there is another version.
Now in the camera motion, you want to say where is the camera?
Sometimes you want to say where is the camera? Yes, in world coordinate. Yeah.
Okay.
What I would like to say, where is the camera and what is the orientation of the camera? This is the degrees of freedom of the camera. Okay.
Okay.
Okay. In version 2, I would like to say something else. I'll take X in world coordinate system, shift it by T, and then rotate. If I do this in block formulation, I'll have X prime equal to R I minus T. And I call this the camera matrix, this, okay, multiplied by X1. Here, the center of the camera in world coordinates is exactly T, and not what we have before. Also, again, C1 is in the null space of the camera matrix. When I write the camera matrix in general block form, M, P4, sorry. M is the first block of 3 by 3, okay? Essentially, in this case, it's R. And, okay, and in the first version, P4, sorry, is going to be T. And in the second version, P4 is going to be R multiplied by T in minus R multiplied by T. Is this clear, the two versions of the camera motions, or camera models?
No.
What is not clear?
What is the difference between the versions? Why you choose the X tag to be different terms in each version?
Okay. First of all, maybe I'll have to say you can move from this version to this version. Okay. First of all, but no problem to move from this version to this version and vice versa. It depends if you like to say that you first take the point, okay, rotate, and then shift. Okay. This is the first version. If this is the version, this is the camera matrix. And if this is the camera matrix, this is the center of the camera in world coordinates. Now you say I have another version. I can take the point, shift it, and then rotate. It's okay. And then you have this version of the camera matrix. In this version, the center of the camera in world coordinate is exactly T. It's not T rotated like here, okay?
So in the different version, you just consider T once in the first world coordinate, the original world coordinate, in second in the camera coordinates.
Please repeat, I didn't hear you well.
I say that the essential difference between the version is that you choose T to be in the first version in the world coordinates, in the second version in the camera coordinates. Correct?
You mean that T plays different roles in the two versions. In the first version, T is called translation, and the camera coordinate, the center of the camera in the world coordinate is T rotated. In the second version, T is exactly the position of the camera in the world coordinate system, and you don't have to rotate it. This is the difference. In any case, when you have camera metrics, which I denote here by M, P4, M is 3 by 3, P4 is the fourth column, vector of size 3, C, which is the camera, the center of the camera in world coordinates, C1 is in the null space of the camera matrix, in any case, like if it's here or if it's here, okay? If I denote the camera matrix in this general form, okay? This is that's it, the result. In any case, you can move on between version 1 and version 2 and vice versa. Sometimes you have papers that use version 1 and sometimes you have papers that use version 2. Okay.
Why R transpose X prime is zeroed?
What?
In the previous slide?
In this slide?
The previous?
Yeah.
Yeah, you said that R transpose X prime is zeroed.
Because if I want to calculate the camera center and world coordinate, then I would like the camera center in local coordinate are exactly 0, right? Because the camera center is located at 0. And this cancel out. Is this clear?
I'm trying to think about it analytically. So
maybe let's move on, Nadav. Maybe let's move on and make it maybe later on, because we have a lot of material to cover. So let's move on, and then maybe take it offline, okay? Okay. So actually, the camera metrics have some properties. Let's discuss them. So because we have few ways to write the camera metrics, I write it in some general form, M P4, where M is 3 by 3 invertible and P4 is a vector of length 3. Later on, you will see that this is not related only to these two versions, it's also related to some inner parameters of the camera. And I would like to write it like this. This is a matrix of size 3 by 4. It's not written here, maybe I'll write it now. Okay. Then let's understand the properties of the camera matrix. So if rank P, since M is invertible, rank P is 3, and therefore the null space is exactly 1. And like what we saw before, the camera center C is determined by being in the null space C1, by being the null space of the camera. And actually C is exactly this, minus M inverse of M times P4. Okay, we saw it just in a slide before. Okay. Okay. Moreover, if I'm writing the camera matrix like this, like 3 by 4, and each row is denoted by P1, P2, and P3 correspondingly, I would like to say something more about the principal plane. Recall that the principal plane, what is the principal plane? Everybody remember what is the principal plane?
What is principal plane?
Z0.
Z equal to 0. The principal plane is that runs through the camera center parallel to the image plane. Okay? So every point that would be projected to the principal plane, okay, the third coordinate, because it's Z equals 0, would be 0. Which means that if I'll take the third row of the camera matrix and multiply it by X, I'll get exactly 0. This means that the third row of the camera matrix stands for the vector that represents the principal plane of the camera. This is the first result. The camera matrix has this property that the third row represents the principal plane. So we have some representation for the camera center, and we have now representation for the principal plane. In addition, if you remember before, we spoke about the rotation matrix, and that the rows of the rotation matrix are actually the representation of the local coordinate system in the global coordinate system. Therefore, the Z direction, okay, if I'm looking at the Z direction, the third row of the matrix M, which is 3 by 3, is actually the Z direction, or the principal axis, which and this represents this is the vector M3. The third row of M is the vector that represents the direction of the principal axis. Okay, this is the principal axis. This is related exactly to what we said before about the rotation matrix, that the third row represents the Z direction, the principal axis. It's exactly like saying what we said before. Okay. Also, we'll have some exercise about this, so I think it will be more clear during the exercise. Okay. Okay. here you have some exercise to do at home. You can, it's easy, you can try to do it. Okay, now I would like to speak about depth of a point. It means that I would like to say what is important to understand. When you have many cameras and you have some 3D structure, you don't see all the points, okay? So you would like, at the moment, when you have some certain camera, to understand if the 3D point is in the front of the camera or back of the camera. What is in the front of the camera? In the front of the camera, it means that the point is in front of the principal plane of the camera. This is the principal plane, z equal to 0, okay? So actually, it's very easy to do it. Why? Because we can take the point in 3D, if we have a point in 3D, and we take the third row of the camera matrix. If we take the third row of the camera matrix and multiply it by the 3D point, okay, the homogeneous coordinate of the 3D point, we get the third coordinate, okay, in terms of the local coordinate system. This is what we call x3 prime. So if x3 prime is positive, then we are in the front, this point is in the front of the camera, of the local camera. If x3 prime is negative, it means that this camera do not see this point. And geometrically, okay, if this is the center of the local camera, of the center of the camera, and this is the principal axis of the camera, and this is the 3D point, then actually x3 prime is the projection of the 3D point on the principal axis. If this is positive, you are in the front of the camera. X is the front of the camera. If x was behind the camera center, then you will get x3 prime, which is negative. This is the way that you can distinguish when points where points are in front of the camera or behind of the camera.
But actually, you don't know the depth of x, no? Or in this case, you know.
What is it?
Actually, you don't know the depth of x, or in this case, you know the depth.
This is exactly the depth of x. Yeah, this is the depth of x when you look from the local camera. Okay, so if you look from the local camera and you take straight line, which is perpendicular to the image plane, this is exactly the depth of the point.
And I understand that. So you assume here that you know the third coordinate of x in the world coordinates?
No, what I assume here, that if I know x in global coordinate, this is x in global coordinate, right? Okay, if I know x in global coordinate, and now I'm asking whether this point in the whole 3D structure is visible from this specific camera, I can answer the question by multiplying the third row of the camera with x and 1 and get the third coordinate in local coordinate system of this specific camera. This is the depth of the point in this specific camera.
Yeah, I understand. Thank you.
Okay, no problem. So we discussed so far the external parameters, which means that I have a global coordinate system and I would like to move to local coordinate system. This is the reference system and this is the local coordinate system. I have many local coordinate system when I have many images. I have one global coordinate system, reference system. Now, since here we are in the real world and the projection of the 3D points are to the image plane, and the image plane is given in some length units, meters, centimeter, etc. But in real life, we have camera, and the camera is attributed with pixels. Okay, we know that we have some pixel by some pixel. Therefore, in addition to the external parameters, we introduce the notion which is called inner parameters, denoted by K. Okay, and this K let me the option to move from length unit in the real world to pixels in the camera. Okay, so let's dive into the parameters of K to understand what is going here. Okay, is this clear? I guess yes. So let's describe the inner parameters. So I'm repeating here. We are going to describe what is called camera calibration matrix, denoted by K. And the camera calibration matrix moves only between 2D and 2D. The 3D was characterized by external parameter R and T. K move between the 2D to the 2D. Okay? Let's describe it. So actually, to recap, to understand what is going here, let's say again, we have a 3D point in world coordinate denoted by x1, x2, and x3, and we add 1 in order to write it in block formulation. This is the camera matrix that you are familiar so far. Now, okay, we introduce linear mapping K, okay, which multiply the camera matrix RT, and this K moves us from the 2D image plane embedded in the 3D plane to the real image of the camera. And now, okay, the x, small x, okay, the projection in the real image is P times X, where P now is, well, the camera matrix now is actually K times R times T. And let's characterize the degrees of freedom of K, okay? So just, we know that we have the camera equations. We say that we have a point in the world and the camera matrix, which multiply the point in the world. By doing this, we get the projection of the point to the 2D plane, multiplied by some lambda, where the camera metric is denoted by K times R times T. So I'm repeating in order to that everybody will be on the same page. This is the thing that I just said before. So X is a homogeneous coordinate of a 3D point. R and T encode the external parameters, which are the orientation of location of the camera with respect to some reference coordinate system, what we call global coordinate system. Somebody has to mute okay. So this is the way we encoded the motion of the camera in the world. Now we have two interpretations to this formulation RT times X. From one side, this is the 3D coordinate of the scene point in the camera coordinate system. And if you remember, the other side is that we get the projection of the point onto the image plane, what we call the homogeneous coordinate of the projection X onto the image plane. So remember always that RT times X has from one side, as we saw in the first few slides of the lecture, from one side it is the 3 coordinate of the scene point in the camera coordinate system, and from the other side we get the projection of the points onto the image plane. Is this clear? It's important to understand.
Why the smiley is sad?
What?
Why the emoji is sad? The first one?
Why it is sad? Okay, good question. Okay, it is sad because it's one interpretation that I'm not going to use it now. I'm going to use the happy interpretation, which means that this is the homogeneous coordinate of the projection X onto the image plane. Why? Because now, if I'm looking at it like the projection on the image plane, I would like to say that the matrix K transforms the image plane, which embedded in R3, from length units to the real image coordinate system given in pixels. This is the reason. To be sure that everything is clear, let's recap what I've just said in the few last slides. Okay, we have a reference global coordinate system, something which is fixed and I do not touch it. Then I have many cameras. For example, I have one camera here, and to move from the reference global coordinate system to the local coordinate system, I have external parameter, which we called R and T. Then this 2D image plane is transformed to the image coordinate system of the camera itself. This is in R3, in length unit, and this is in pixels. And K is the mapping between this 2D to this 2D. So all in all, I have K times R times the block RT. Okay? This is the camera matrix, and let's dive into the properties of K and the degrees of freedom of K. Any questions?
Yeah, here as K is linear, so it means that the real image here is infinite, right?
The real image is infinite. What do you mean by that?
That
the image is not infinite. The image is finite. It's the CCD of the camera. This is the image. Maybe
the number of pixels is finite?
The number of pixels is finite. Yeah, you have CCD of the camera. You have sensor of the camera. You have 100 by 100, I don't know, pixels. This is finite, yeah?
Oh, so how can we map the image plane, which is infinite, to a finite image, real image with a linear mapping?
Okay, let's try to follow my the characteristic of K, and let's see if it's clear enough. It's not clear enough. Let's move. Let's try to understand again what is happening there. Okay. So first of all, we have something which is called the focal length. Okay, of the camera. And actually, if you remember in the first or two slides of the lecture, the focal length of the camera is actually like saying that the image plane is located at Z equal to F. Like what you see here. Actually, it should be written here, Z equal to F. Or like what you see here. Okay? And this is the way that you can move from Z equal to 1 or to Z equal to F. Okay, this is one thing. Actually, I would like to say that F rescale the images in the sense that I'm moving from meters to pixels. And the way this is done is by introducing another parameter, which is called number of pixels per unit distance. And if I would like to move from length unit to pixels, then I would like to multiply everything by M, like here. Okay, so I have parameter which is called M times F, which is just 1 degree of freedom. So let me make an abuse of notation and forget about the M and stay with the F and say that F rescale the image from meters to pixels, like here. Okay, so this is the first degree of freedom. Okay. Okay, now generally the principal point in the real world is centered at is located at 0, 0, 1, like here. Okay, but in real cameras, we would like to enumerate the images that such that the 0, 0 is located in the left corner, in the left upper corner, left bottom corner, never mind. In order to do this, I have to add some shift to the coordinates by adding x0 and y0. Actually, x0 and y0 is the location of the principal point in the image of the camera. Okay, in the real image, which is in pixels. Okay, this is x0, y0. Okay. This is the way I'm moving from one origin to the other origin. Okay. Okay. Moreover, pixels are not always squares, but can be rectangular. In order to compensate about this, f is multiplied by some gamma. Gamma compensates for the non-equal, I would say, non-equal measure of a pixel in the dimension. Okay, so I introduce also gamma. So I have gamma f, x0 and y0. In addition, it sometimes happens that the pixels are not just rectangular, but maybe tilted like this. If they are rectangular, then s equal to 0. Okay, because I have angle of 90 degrees. And then this is omitted, but if they are tilted, I introduce the arctangles of 1 over s, okay? And I put it here, the s here, to compensate for the angle. I think this is rarely used, that's what I know. But in order to understand what is exactly the calibration metric scale, let's try to recap everything and to understand how many degrees of freedom I have in the camera. So I have r, t times k, and p is of size 3/4. So I can have maximum 12 degrees of freedom, right? So the rotation have 3 degrees of freedom, right? And the translation, t, how many degrees of freedom we have in the translation?
2.
3. Okay. Okay. Then.
Why 3? Because the ambiguation of minus and plus.
No, 3 because it's T1, T2, T3. Okay. Then I have the calibration metrics. Let's say count 1, 2, 3, 4, 5. 5 degrees of freedom. It means that we have 11 degrees of freedom out of 12 entries of the camera metrics. And this is since any multiplication by non-zero scalar product, scalar over the matrix, will give me an equivalent matrix. This is since the projection of the camera matrix is obtained in homogeneous coordinates, which means that we divide the resulting vector, which is 3 coordinate, by the third coordinate, and therefore p and p times some alpha is the same p. So therefore we have only 11 degrees of freedom. Okay? This is the enumeration of the number of degrees of freedom of the camera. I'm not sure about the time. Okay. Would you like to have some break? Or you would like to continue?
I prefer break.
Prefer break. Okay, so let's have break. I'll pause the recording and let's be back, please, in 5 minutes. We'd say 5 minutes. I'm not sure about the exact hour. What is the exact hour? I'm not sure.
It's 10:15 now.
It's 10:15 now? Okay, so let's be back at
10:20.
10:20. Okay, thank you. 10:20, thank you. אוקיי, אני אדלג על זה מפאת קוצר הזמן, זה יהיה לכם אחר כך בשקפים. אני רוצה להגיד שני דברים.
No, it's the English, right?
סליחה. Okay, sorry. So recap the issue of depth of a point. And first of all, a calibrated camera is a camera which I know the internal parameters, which I know K. And then if I know K, I can cancel out K, the inner parameters. And a calibrated camera is of this form, okay? Which I have only the external parameters. So we saw that for a calibrated camera, we know how to calculate the depth, okay? I hope it's more clear now. If I have a 3D point in the world, okay? I have this, 3D point in the world, and I would like to know if I see the point from the camera, which means that the point is in front of the principal plane, which is D0. I know how to do it by looking at the third coordinate of the resulting multiplication between P and X, which what is written here. And this is fine. I hope everybody understands it now. But what happens if I would like to understand if the point is in front of the camera where the camera is uncalibrated? What do I mean by uncalibrated? Uncalibrated means that I do not know the calibration, internal calibration matrix K, which means that what I get is this, something which is 3 by 3 matrix and fourth column, okay? That's what I see. This is the general form of the camera. I don't know K. I know just P, which is 3 by 4. So it turns out, and you will have it as an exercise to show that if we take the camera matrix and we normalize it such that the third row of the 3 by 3 part is such that the norm of it is 1 and the determinant of M, the 3 by 3 part, is positive, then it can be shown that the depth of the point X, okay, this one, the depth of the point X is exactly W, where W is just the third coordinate of the projection when I take P and multiply by X and 1, okay? So as I have in the calibrated case, when I know K, I also have a way to understand if X in the front of the camera or in the back of the camera by making this calculation, okay? Under the assumption that M, or the camera metric, is normalized in terms of what is written here. You will have it as an exercise to show it. This is called chirality. Chirality, the depth of the point in the uncalibrated camera setting. Okay, so in a minute you can see that if the camera was calibrated, which means that if M was exactly R, then we immediately have this relation that the third row is 1 and the determinant is greater than 0. And actually we exactly have what we have before, which is W is X3 prime, what we have before. So we'll get it as an exercise and I hope it will be clear and you can do it, okay? So let's move on. Just let me to clear all drawings, just a minute, okay. Okay, so I would like to move forward to the second topic of this lecture, which is projective geometry. So recall that I have camera equations, which I write like this: P times X, P the camera matrix, okay? X is the projected point on the image plane, and lambda it's the scalar that we have in front of it, okay? Okay. So the perspective projection, okay, of a point X in the world to the image plane, little x, is actually given by multiply X by P and divide this resulting 3D vector by the third coordinate, like what is written here, okay? Okay. Now I have a question, okay? And my question is the following. What is the role of lambda? What is lambda?
It's array.
What is it?
Array.
Lambda is a scalar, right?
Yeah.
Lambda is a scalar. And what is lambda? What is the role of lambda? What do I mean by that? Each point on this viewing ray, right? I have each point in the 3D space in this viewing ray is projected actually to the same point here, x, right? But essentially, each 3D point will give me another lambda, right? Do you understand? I have this viewing ray, and I take point on this ray and project it to the image plane. Actually, I'll get the same projection for all the points through this viewing ray, here and here and here, right? But the lambda, the scalar in front of the projection, will be different. Do you agree? Is it clear? Clear or not? So, yes? Yes, okay. In some sense, actually, it means that all the points on the viewing ray are considered the same point, right? All the points are projected to the same point, right? The question is, can we formulate mathematically this situation that a whole bunch of 3D points on a viewing ray are projected to the same point in the image plane? This is the first question, which it's supposed to be motivation to the projective geometry. Okay. So another question is that if I have some parallel line in the world, okay, they are projected by the perspective projection to line which are not necessarily parallel, right? And again, can this formulate mathematically? Also, line in the 3D world is projected to a straight line in the image. Also, can it formulate mathematically? So the idea is the following, that the way to access this observation mathematically is actually by introducing tools from the projective geometry. And specifically, we are going to cover the idea of homogeneous coordinate in points and line in the projective space P2. And we'll cover also the idea of projective transformation, okay? So let's start with homogeneous coordinate, which we touched it in the beginning of the lecture, but I want to make it, how you say, mathematically, I want to make mathematical definition for the homogeneous coordinate. So if I take two vectors, x and y in R3, I would say that they are equivalent if there is some scalar lambda such that x equal to lambda times y. Lambda is not 0, okay? These points are going to be equivalent, okay? So these two vectors, x and y, which are distinguished by just scalar lambda, represent the same element in the projective space P2. That's what we say. Now the projective space P2 actually consists of all the elements that exist in R3 when we are excluding the 0, 0, 0 point from the projective space. Later on, you will understand why we excluded this point. Okay, so actually, I have some space which are called the projective space P2, and the way that I represent the point in this space is by using a vector of length 3. Okay, how? But what I'm saying now is that all these points are the same element in P2. Can you say why?
They are in the same class, no?
Same class. Why the same class?
They scale. They scale.
They scale. Okay, the second point is 2 times the first point. The third point is 3 times the, okay, etc., etc. So they are the same element in P2. And also we say that all these elements are the homogeneous coordinate of the point 3, 2 in R2. Why? Because if I take this vector and divide it by 2, I get exactly this vector. And if I take this vector and divide it by 3, the third coordinate, I get back this vector. Okay? So to define it, the homogeneous coordinate of a point x1, x2 in R2 are actually all the representation kx1, kx2, and k such that k is not equal to 0. Okay? This is so every point in R2 has many representation as homogeneous coordinates, okay? And vice versa, if I have homogeneous coordinate written here, I can go back to x1 and x2. Okay. Is any triple can be represented again as a point in R2?
No, you said that each point on the z equal 0, so can't be represented, including the region.
Right. So there are points in R2 that not correspond to any point which can be represented by a triple, like x1, x2, and 0. Because if I'm going to take the 0 and divide it by divide x1 and x2 by 0, I'll get something which is infinity. It's not included in R2. And actually, this is the main difference between the projective geometry and the Euclidean geometry. The inclusion of points in infinity. So, to say it more formally, 2 lines in the Euclidean space in R2 almost always meet at a point, right? However, parallel lines do not intersect. We say that they meet at infinity. That's what we generally say. So how we are going to get we are circumvent this situation by the addition of what we call infinity points or ideal point to the projective space P2. Okay. And in general, we can do it also to not just to P2, but to P2 to power of n. Okay. So, having said this, let's try to have some homogeneous representation to lines and points. Okay. So a line in R2 is represented as we know. Okay. Like dot product between A, B, and C, and x in x1 and 1, okay? Ax plus by plus c equal to 0. So any line in R2 can be represented by ABC transpose, except the 0, 0, 0 transpose, okay? Just a minute. Just a minute. Okay. So ABC transpose is a representation of the line, okay? However, the correspondence between the lines and the vector is not one-to-one. I would say that there is equivalence class such that if ABC is a line, so also KABC transpose is also the same line. Because if I multiply this equation by K, it still will be 0, right? So in general, I would say that a line is represented by ABC and K times ABC. This is the equivalence class. And since 0, 0, 0 transpose does not represent a line, actually it's excluded from the P2 projective space, okay? So the set of equivalence classes of vector in R3, excluding the 0 point, forms the projective space, okay? So we see that lines are represented by triplet and by the equivalent class, and we know that if I'll take now look at the point that given in R2, let's call it XY, and the point resides on the line ABC, then it turns out that if I'm writing XY in homogeneous coordinate like this, okay, this is formalization of homogeneous coordinate, and I'll multiply it by the line, then I can say that each point resides on the line if and only if the dot product between the line and the homogeneous coordinate of the line are exactly 0, right? Okay. However, the equivalence class of this homogeneous coordinate representation of XY also satisfy the equation of the line. So all in all, we can say that points and line are represented by homogeneous vector, which are essentially elements of P2. Actually, points and lines are represented by triplet, and they're represented by equivalence classes, as we saw before. Okay, just a minute. Let me clear it. Okay. Okay. So this is repeating, but just to say that the set of equivalent classes of vector in R3, excluding the 0, forms the projective space, where the lines and the points are represented by what we call homogeneous coordinate. Points are dual to lines in the projective space, and there is something which is called the duality principle. It means that to any theorem of that for the two-dimensional projective space, the corresponding dual theorem, which can be derived by interchanging the role of points and line. For example, two lines intersect each other in one point, and the dual theorem is that for any 2 points there is one line going through them both. Okay, this is the duality principle. So a point in P2 lies on a line in P2 if and only if the dot product is exactly 0. Okay. The intersection of two lines, L and L prime, is the point, is the cross product between L and L prime. It's very easy to show it using the triple scalar product. So the claim here that if I have two lines, L and L prime, I can calculate the intersection between them, and the intersection is the cross product between them. And how we prove it? We define X to be the cross product, and we use the triple product property, which means that A times dot product cross product is actually the same as a circular shift of this equation. Means take C, put it here, and move to the right the equation, and then this is actually equal to C times A cross B, etc., etc. Okay, I guess you're familiar with this. Okay, now I'll take this definition of X, I'll multiply by dot product multiplied by L, and using this identity I'll get exactly the 0. This means that X, which is this, actually lies on L prime, lies on L prime. Okay, and also now the other derivation. Let me explain that X reside on L and reside on L prime. Okay.
What is X?
What?
What is X?
X is written here. Is the cross product between the lines.
What is cross product?
What is cross product? Cross product geometrically, it's the vector which is perpendicular to the plane spanned by the two vectors in R3, and the magnitude is proportional to the magnitude of the parallelogram which created by these two lines. And algebraically, in a minute, you will see how you calculate the cross product.
Okay.
Okay, so since the dot product between the x and the line is 0 and the x and the other line is 0, we conclude that x reside on L and reside on L prime since it is 0. So we showed that the intersection of two lines, L and L prime, is the cross product between these two lines. And using the duality principle, the line through the 2 points x and x prime is exactly the cross product between the points. Okay? Just by using the duality principle. Any questions? Okay. So let's make an example. Let's determine the intersection between 1 and 1. The lines x equal 1 and the line equal 1. The line y equal to 1. We know that in R2 the intersection is 1, 1, right? So let's see that what we get exactly using this calculation. So x equal to 1, the line x equal to 1 is exactly minus 1x plus 1 equal to 0, and therefore by homogeneous coordinate it's minus 1, 0, 1. Okay, A, B, C, like what we had before. Y equals to 1. This is the representation of y equal to 1. And therefore, the ABC is 0, minus 1, 1. Okay? Okay. Now, we know that in order to determine the intersection between two lines, we have to take the cross product between the lines. And how we take algebraically the cross product between the lines. We write it in a matrix, I, J, K. We write the vectors. This is the first vector. This is the second vector. And then we calculate all 2 by 2 determinants, okay? In order to calculate the resulting vector in the first coordinate, we take this determinant of this, etc., etc. And as you see, the point we get is 1, 1, 1, which is, this is in homogeneous coordinate.
But you don't know I, J, and K, no?
Who asked the question?
Jonathan.
Jonathan. Okay. I don't know I, J, and K, but I, J, and K stands for X, Y, Z in the X, Y, Z system of coordinates. Just notation. Is it clear?
No, I don't understand.
You don't understand. I see. Okay. Let's try to explain again. You have 3 vector and 3 vector size of 3, vector size of 3, and I'm taking the cross product between them. Geometrically, I explained before what is the cross product. Okay. Algebraically, how do you determine the cross product? You take the vectors, put them in the matrix. This is one vector, this is the second vector.
Okay.
Now, I would like to determine each coordinate in the 3 vector in the 3 vector that I'm going to take. In order to determine the first coordinate, okay, I'm doing the following. I'm erasing the first row and the first column and compute the determinant of this, and I get 1, right?
Mm.
And then I'm doing etc. I'm doing the same thing. Okay, this is the way that I'm computing the vector. Now it's clear?
Yes.
Okay.
Well, it should be -1, no, in the second entry.
No, like you calculate determinant. You take like you calculate minors. You take the sign of the sign of the minor into account. In the second, you multiply by minus. Okay, let's continue. So this is the homogeneous coordinate, right? And what is the inhomogeneous coordinate?
1, 1, no?
1, 1, exactly. Good. That's what we get, okay? And this is what we're supposed to get because we would like to understand what is the intersection between this line and this line. Okay, let's move on. Okay. 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 Now let's take some other example. We have the lines x equal 1 and x equal 2. Please mute, please. Okay. We would like to understand what is the intersection between the line x equal to 1 and x equal to 2. We make the cross product and we get 0, 1, 0. This is a homogeneous point, but we don't have inhomogeneous representation as we saw before. And the explanation is this is a point at infinity in the direction of the y-axis. Why is it? And understand why is it. Intuitively, let's understand why is it true. So in order to interpret the geometrically 0, 1, 0, let's look at 0, 1 epsilon. Okay, and if we look at 0, 1 epsilon, and we take the homogeneous, we go from here to the homogeneous coordinate, we divide by epsilon, and we get 0, 1 over epsilon, and 1. And then when epsilon tends to 0, we see that we get the interpretation that the point is becoming infinite in the direction of 0, 1. Okay, that's what you see from here. So this is the geometric interpretation of the infinite point. Okay. Just to, okay, let's continue and then I'll say. So if I have parallel lines that have the same A and the same B, like here, and different intercept C, okay, C prime, then it's very easy to show that using the homogeneous representation of this line, the cross product between this line is exactly B minus A0 times some constant. We can ignore the constant due to the homogeneity. And the resulting point is B minus A0. If you think about it, actually, this stands for the direction of the line, for the line which is ABC or ABC prime. Okay. Okay. So let's now take the exact definition of P2. So P2 consists of homogeneous vectors such that the third coordinate, when the third coordinate is not 0, I have a corresponding point in R2, but I extend R2 by adding points such that the third coordinate is going to be 0, and such point with x3 equal to 0 are called ideal point, vanishing point, infinite points. This is the name, okay? So this is the big difference between R2 and P2. And, okay, just a minute. Now, if you take a special care and you ask yourself, does the infinite point lies on some line? The answer is yes. And the lines on the line at infinity, which we call an infinity. Why is this? Because if I take x1, x2, and 0 and multiply it by 0, 0, 1, I get 0. Therefore, all the infinite point, the vanishing point, lands on the vanishing line, which is actually in homogeneous representation, this line, okay? And if you ask yourself again, ABC transpose, where intersects L infinity, so it intersected in B minus A0, the same for L prime, with the same A and B. So L and L prime and L infinity intersect at the same point by B minus A0. Geometrically, this is very nice, I think, drawing. Actually, this is P2. The way to illustrate P2 when you take R3 and you say the following: each ray stands for a point. Each plane stands for a line, okay? So each ray like this stands for a point, actually. And each plane which going through the origin stands for a line. Since the infinite points, the ideal points, have a third coordinate which is equal to 0, any ray in this x1, x2 plane is going to be an ideal point. And actually, if you want to understand which line you represent or which point you represent, you take actually, this is, for example, this one, okay? Just let me show you. This plane, which going through the origin, stands for some line. And if you want to understand which line, you can actually take the plane of the line and cut it with z equal to 1 and understand which line resides on this line and which line is it, okay? So this is some illustration to say that points can be represented in P2 by rays. The ideal points reside here in this part, and the lines are represented by planes or are going through the origin. Okay. Okay. What is the time now? Sorry. Okay. So let's take two or 3 minutes more, and then we can stop and continue next time. So what is here? I'm give you some intuition. Nothing is proved in a mathematical rigid way. Just to say the thing that we see in images. Okay, so we have a plane here. This is a plane which captured in an image, and actually each plane has its vanishing line, which means that if I'm capturing this plane in an image and I'm looking at the convergence of these parallel lines, okay, with this line that were parallel and converging now to a point V1, and this parallel lines which converge to point P2, if I have another set of parallel lines that will converge to another point here, for example, or here, it means that each plane has its vanishing line, okay? Its plane depends on the direction of the plane, you get one vanishing line. All converging points will stay on the same line. And if you want to calculate the vanishing line, the way you do it is the following. If this is the plane in the world with some normal, and this is the image plane, this one, the image plane, in order to understand what is the vanishing line of this plane, you take a plane that goes through the origin of the camera center, and is parallel to the plane in the 3D world, and you cut it, the image plane here, you will get the vanishing line of this plane. Okay, I'm not proving anything, just saying issue that may be interesting. Okay. Now take a look at this image. In this image we have many planes. The left image here in small window, we see that the floor, the tiles on the floor have two directions. I would say this direction and this direction. This direction converging to a point, very far point here, on the vanishing line of this plane, and this direction converging to this point, okay, on the same vanishing line. Okay. Okay. So this is the idea of vanishing line. I would say that the vanishing line of a plane depends on the direction on the plane, not on the position of the plane. And every plane in the world has its own vanishing line, like what we saw so far. This is to conclude. Let me see what we have next, just to, okay. Maybe let's start these topics next time, okay? In order to not make it very fast. It's okay? Okay, I think it's 11, right? Or not yet?
Yeah.
Okay.
Yes, 11.
Okay. So let's stop.